präsentiert von Open Learnware, die Plattform für Lernmaterialien an der TU Darmstadt.
I'd like to welcome you all in this tutorial session on hybrid aerodynamics. I'd like to thank Andrea for inviting me to give a tutorial on a method with this title, which is kind of like awkward, I think, when you think like an AMAM conference, right? I mean, what is this three words have to do with what we want to study and what we want to learn in these conferences? So the reason is basically that this method has been successful in controlling legged systems, legged robots. This legged robot here is Mabel. So we're going to see a little bit of the experimentation that goes behind of implementing this method, but most of this tutorial will be on the theory that underlies the hybrid aerodynamics method. So, and to sort of like to give you some context, I think this is a slide that you must have seen before in presentations by probably Bob Full or Dan Kodicek. So, and I guess there are many people here who do work on these types of hierarchies in models, right? So there has been this hypothesis that was proposed by Blicken, Full, and by Dan Kodicek also in 1999, that when animals of different structures, morphologies, leg numbers run, they effectively tune their musculoskeletal system so that if you see their macroscopic motion, essentially they appear as if they are jumping on a pogo stick, right? So, and they came up with kind of like a 2 degree of freedom simple model, the spring-loaded inverted pendulum, which they called a template, this modeling and control hierarchy. And roughly speaking, what I will be talking about today is some way that you can actually mathematize these hypotheses and use these models basically to control more complete structures, or use intuition that you obtain from these models to control a more complete structure. Of course, I don't know if this hypothesis is actually true. I think it's in biology, so I think it's a matter of you know, current research, and there has been many experiments that try to show if there is any relationship or something like that between simple or lower dimensional dynamical systems and higher dimensional model representations. But in robotics is actually a useful thing because, you know, whenever you have a model that is being composed by masses, inertias, you know, springs, essentially you can actually have these components available and build a robot. So this is, I mean, these are just robots that I've worked in the past. And so what I would like to mention here is that I will not enter anything about sort of like experiments that you can do in biology to observe these types of behaviors. This work will primarily be on feedback control and mathematics basically behind this. And the key idea there is basically that you can actually reduce the dimensionality of your problem by using feedback. And that's a closed-loop control system, so you are measuring sort of like your state, you're processing it, you're computing things, and then you're feeding things to the system through the actuators. And the main sort of like hierarchy that we have here is that we have a lower dimensional dynamical system, which, you know, you can think of it as a template, that essentially describes the dynamics of the behavior that you want to have. And the question is, how can you coordinate a higher dimensional dynamical system so that its behavior is governed by this lower dimensional sort of like target dynamical system? Well, maybe it's a little early to start with this, but I'd just like to to point out, I mean, many of you who do simulations in models, essentially, it all boils down, if you want to study the stability of a periodic orbit, into, you know, getting access to a Poincaré map, then linearize this Poincaré map and computing eigenvalues. So essentially what we will do here is a similar thing. So you will have a Poincaré map. I mean, forget about the details. We'll see what this is. So essentially the Poincaré map advances the state of the system from the kth step to the k+1 step. And if you linearize this Poincaré map with the method that we're going to see the details in this talk, essentially it takes this sort of like block triangular structure So, and whenever you have like such a structure, essentially the eigenvalues that are associated with the Jacobian of the Poincaré map, they are the eigenvalues of this term here and the eigenvalues of this term here. And these have very clear interpretations in terms of this anchor template type of hierarchy in some examples. So this one is actually going to be your lower dimensional. So let me start from this. So this is your higher dimensional system, like what is it, the orbit that you want to study in your actual model representation. Now, this term here essentially would correspond to the lower dimensional system. And this term here is tunable, corresponds to tunable transverse dynamics. So what you have is a parameter, a variable here, and you can make this exponential decaying fast as you want, basically, so that you can push all the eigenvalues that are associated with this part inside the unit disk. Then basically you can see that whatever the stability of this system is, it basically depends on the stability of this lower dimensional system. So this is the hierarchy that I was talking before, that you can actually have a lower dimensional dynamical system governing the stability properties of a higher dimensional, more complete model representation. Of course, we need to talk a little bit about how we can actually bring the system to this form. So a little bit about the history of the method. So the method has started by Jesse Grizzle. He is a professor at the electrical engineering department at the University of Michigan. So he was on sabbatical and he got introduced to this. He was on sabbatical in Strasbourg, and he got introduced in this bipedal robot. The name is Rabbit of this biped. So this is a 5-degree of freedom bipedal system. We are talking about the degrees of freedom when the leg is in contact with the ground. And it has 4 actuators. It has only rigid links, no springs in this particular structure. And essentially the point of contact with the ground is a pivot, a passive pivot, so it's an actuated. And there is also a boom that holds the system, stabilizes the system sideways. So he implemented that method, basically, or he introduced that method with the help of his student, Eric Westervelt, who you can see here in this video. And this is a video of Rabbit walking, of course supported by the boom, in its lab in France. So what I'd like to mention here is basically how naturally this system recovers from perturbations that Eric actually implements on the system. So you will see actually that he will push the system, he will hold the system until it stops, and then the system comes back to its periodic orbit. And also the whole behavior is actually robust to parameter variations, because what you see here is an additional weight that the controller is not aware of. So essentially you can have parameter variations in terms of like changes in the masses and inertias, and the system can actually take care of those things. So this has been successful in terms of walking on rigid robots, and the setting again is you have n degrees of freedom, n-1 of them are actuated. And that success in walking prompted basically a collaborative effort with Jonathan Hurst. Then he was a PhD student at Carnegie Mellon University. Now he's an assistant professor at Oregon State University. And he designed a robot which is called Mabel, which is essentially a very it's a big robot with springs. We will see it in the next picture. So those bars that you see here protruding from the robot's body, they're essentially very large springs. And the mechanical system is organized in such a way so that when the knee bends, essentially these springs bend, therefore storing elastic energy, which is then released in a later part of the motion. So these are springs that can be used, they're large enough to be used for energy storage. The robot is actually very big, as I mentioned. The distance from the hip to the toe is approximately 1 meter. It's 1 meter when the leg is extended, and it's a 65 kilos robot. So it's actually, well, not my weight, but it's getting there. So it's again constrained to the boom, so the controllers worry about sagittal plane stability. They don't worry about lateral stability, although there are extensions of this method in a three-dimensional context. And again, we have a passive pivot point. And this is a video of the robot actually running. Here is the two PhD students, so Kaushal Srinath and Hyewon Park. Hyewon is with Sangbhai Kim at MIT, a postdoctoral student now, a postdoc now. So this is this is Mabel starting from a walking gait, switching to a running gait, and we will see that it's going to pick up speed actually, and the running is going to be, so the peak speed here is actually 3 meters per second. The average speed is about 2 meters per second. It's absolutely amazing to see this thing actually running like this in the lab. I mean, it's a big robot. You can actually, it's like double the size of me if you take it like sideways. It's as tall as I am, and it's about like 65 kilos, and it makes a lot of noise when it does these types of motions. So this is a result of applying the method to a compliance system, or a version of the method that can accommodate actually springs and compliance. And I would like to stop this video and start with an overview of this tutorial session. So, this is kind of like a modular presentation. I mean, we've heard about modular robotics yesterday in the Lokomov project. So there are like 4 modules. So the first one I will talk about modeling. The method is primarily model-based method, so let's see what the models are. Control synthesis, so what is the structure of the controller that actually makes these systems work. And, and then we go into control design. So I separate synthesis from design, because synthesis has to do more of the structure of the feedback, while design has to do with selecting particular parameters and implementing this feedback. And then I will talk about, if we have time, on how to actually incorporate springs and the slip embedding type of constraints. Then at the end of this part, whoever wants to actually have an experience of implementing this method on a simple 3 degree of freedom walker, there are some MATLAB files on the web. If you can download them. And I guess whoever wants to participate in that, will go through these files and try to make a 3 degree of freedom biped walk using the method. So the first part, models. And actually that's what got Jesse Grizzle intrigued with these systems, is basically that these systems are hybrid. And when we say hybrid, I mean, I guess there are many ways to interpret what hybrid means, but when we say hybrid in control systems, we mean systems that combine continuous time dynamics and discrete time dynamics. I mean, if you think of a walking robot, essentially it evolves in continuous time and during a swing phase, and then when you hit the ground, you have a reset. That is an event-based thing, so it's a hybrid system, and it's also an under-actuated system. So that means basically that you have less degrees of, less actuators than number of degrees of freedom. So these things actually make, I mean, of course it's non-linear and all these things, but these extra properties make these things notoriously hard to analyze. So let's start with kind of like seeing what the main model is. So you can think of a walking gait as an alternation of single support phases where one of the legs is on the ground and the other one is in the air, and a double support phases where both legs are on the ground. So during the single support phase, you can actually use Lagrangian dynamics to come up with a representation of your system, which is, this familiar set of equations. I'm sure you have seen this, so I'm not going to get into too much detail. So mass matrix, velocity dependent forces, configuration dependent forces, and inputs. Then when you hit the ground, basically you have impact dynamics. And this impact dynamics essentially under appropriate assumptions, and of course this is just a model, it's not supposed to capture every single detail of the interaction between the foot and the ground. So this phase will be assumed an instantaneous phase, which means when the leg which is in the air touches the ground, at this very instant the leg which was on the ground essentially moves in the air. So we compress this double support phase which is into a single event basically, which is of course maybe not so biologically true. Of course, these have finite durations, but in modeling these systems and in bringing these systems into a convenient form and approximating basically what's happening, this is a sufficient, at least for this work, assumption. So what you get is basically a mapping. Now this is an algebraic mapping. I mean, there's no differential equations involved. Essentially it takes the position prior to the impact into a position after the impact, and it takes the velocity prior to the impact into a velocity after the impact. And if you put these components together, essentially you have something like that, and we will see this basic figure coming up in this talk. So we have a single support phase in which you have these dynamics evolving continuously, and then once you hit the ground, you have a discrete event, a double support phase, which basically takes the exit conditions and updates them with entry conditions. Basically, it resets the initial conditions of the continuous dynamics. So in mathematics, I mean, if you bring this into a state space form, essentially it takes this form. So the method, of course, it's not like, I mean, you can expand it to accommodate gates that have multiple continuous phases. I mean, this is, for instance, what you would do in a running phase, where you have like a flight phase, where you have a stance phase, and you have, so you can extend it like that. And also you can extend it in you know, accommodating finite time support phase, double support phases in walking. So anyway, the second part that I would like to talk about the models is under actuation, and that has to do basically with the dimension of the input versus the dimension of the configuration space, the dimension of the degrees of freedom basically here. So it has to do with the joint angles and velocities and the inputs. So if you're fully actuated, like this system, essentially you touch the ground, you have a flat foot here, and if you sort of like tune your controller appropriately, essentially you can continue having a flat foot here, and then you can actually use your ankle torque to do some control. So that would be a fully actuated system, because you do have an actuator to actually control all these degrees of freedom basically in the system. However, in our case, you know, while, I mean, this is a common assumption if you think of the zero moment point and how humanoids walk basically. But in our case, we want to actually remove this assumption, which can be actually, I mean, it can make control things easier, but it's not too realistic when you think of portions of the gates where you may have, you know, a heel strike, so you don't really have your leg flat on the ground or a toe off. So essentially, we will approximate everything with a passive pivot, so that's just a passive unactuated joint here. And then this makes the system under-actuated in the sense that the dimensions of the inputs, or the number of the inputs that you have, which means in this system you have one actuator that basically sets the hips, basically the left and right hips, and then one more actuator for the knee and another actuator for the knee of the leg, which is in the flight. So we have 4 actuators here, and then we have 5 degrees of freedom, so obviously this is an under-actuated system. So I mean, we will see these things. I'm just introducing the models here. We will see them more carefully as we progress through the lecture. And by the way, I mean, I didn't say that at the beginning, but I'm sure there are people probably in the audience that have tried to implement this method. So if you have questions, just feel free to ask them during the tutorial, so you don't have to wait until the end. So I kept this modeling part a little bit short. We can talk about it maybe afterwards, but I did this because I want to jump into the feedback synthesis, which is essentially what the hybrid aerodynamics is. So let's just think of, let me just introduce the key ingredients, the key ideas that are behind this method. So the first idea is basically the idea of virtual constraints, and that's associated with dimensionality reduction. Remember, I told you at the beginning, you have higher dimensional systems, lower dimensional systems, so there has to be some dimensionality reduction going on. And the key idea here is basically the notion of a virtual constraint. So just to give you an example, if you think of this 3 degree of freedom piston, and you have completely unconstrained motion, and you let it go from some initial condition, this thing is going to do something, I don't know, very interesting, but it's not essentially a very organized motion, so this can actually change. If you let it go, it will do crazy things. But if you introduce 2 walls so that you restrict basically the motion of the system so that it's always, I mean, this part of the system is always in contact so that it's always level, right? So the piston here remains always level, and then always moves along this line, you'll see that the motion is, of course, and you expect that very, very different. So this is essentially a 1 degree of freedom system. So you have like this 1 degree of freedom continuously, this is continuously increasing. You can think of it as an internal clock on the system, and then the whole system is essentially coordinated with respect to this variable and goes up and down, and we will see what that means mathematically. So let's go back in this picture. So if you look at this constrained version of the piston, so this 1 degree of freedom system, essentially the cylinder walls impose 2 constraints, so you cannot really move sideways, and you have to move in a way so that this point is essentially at the same vertical line with this point. And of course this means that you can actually find relationships between these 2 degrees of freedom here, the theta 3 angle and the theta 2 angle, based as functions of the theta 1 angle, right? So, and if you go through the geometry, this just merely expresses the fact that this stays level and this moves up and down in this red line, the vertical red line. Now let's think of a similar situation in the other side, where you have 2 of those degrees of freedom actually actuated. So you have torques that you can apply at these joints, right? And then let's take this constraint here and write it in this form. So essentially, let's just try to see if we can measure the difference between the angle theta 2 and theta 3 and those functions that are essentially correspond to the constraints that are imposed by the cylinder walls. Now, if you can design a controller that uses your actuators in a way that it drives this output to 0 in an asymptotic fashion, essentially this picture here is not going to be very different from this one once sufficient time actually goes by. So essentially what you've succeeded with this little control prescription is that you take a system which has 3 degrees of freedom in its completely unrestricted, unconstrained motion, and essentially you force it to follow or to be compatible with constraints that are in this system, and basically have a motion that corresponds asymptotically to a 1 degree of freedom system. So there is the dimensionality reduction. So essentially, instead of having, physically, the constraints, instead you physically impose the constraints on the system, essentially you can do it by using your actuators and imposing particular relationships between your degrees of freedom and what you want to have basically as a desired constraint behavior. So this is asymptotically in 1 degree of freedom piston, and of course it behaves in a very different way if you actually close the loop. So this is a little video of how it will actually evolve. So it starts off, but eventually as time goes by, it converges to something which is effectively indistinguishable from what a 1 degree of freedom piston would do. So this control algorithm takes care of this. I'm not going to get into the details because we will see these things in subsequent slides. So essentially what you do is you are measuring those theta 2 and theta 3 angles, and then you are comparing these theta 2 and theta 3 angles with something that comes which is the desired, the virtual constraints, and then you take their difference and you can actually implement a PD controller or whatever you wish basically to push the system operate in this way. So let's see this thing a little bit more. So what I would like you to notice here that this is monotonically increasing strictly with, is it a question or something? Okay, let me just stop this video. Yeah.
Just a short question.
Yes,
you
please.
said that a PD control is enough, but this means that like the relation is always something like decreasing or increasing, so it's not like rather like non-monotonic. So that assumption is true or not?
So, there are various ways to impose the constraints, right? So you can pick whatever control method you want actually to do that. You can actually put Lyapunov functions, or you can use feedback linearization. That's what I'm going to talk about. So that doesn't have to do with the way that you necessarily parameterize the output. But in this actually, what I will show is that the way actually that you parameterize the output is actually going to be very, very important in actually reducing the problem into something that involves only functions of the configuration variables and only functions that can be interpreted as physical holonomic constraints. What I'd like to mention in this video basically here is that if you see it again, you'll see this angle here continuously increasing, strictly monotonically with time. So, and everything else, you know, sort of like this was the angle of the crank, right? And the other angles that are associated with this link and this rigid body here, they are essentially coordinated with respect to this rotation here, so that this system goes up and down. So this actually looks like this situation where you have sort of like a system, a biped, and you can see in a stance phase how this angle actually increases. So you hit the ground at a particular angle, and then as the motion progresses, essentially this thing continuously increasing. And this angle, essentially, it will play. I mean, I want you to think of it like that. It will play the role of this crank, and it will essentially define an internal clock for your system. With respect to this internal clock, the entire system actually coordinates. So, and this is actually something that we will also see in subsequent slides, because I believe that, you know, once you see something once in a presentation, I mean, it's good to see it again and how it works. But I would like you to keep this in mind, that essentially we coordinate the entire system with respect to an internal variable. This is the angle basically of the leg that is sort of like connecting the toe with the hip. So it's not like a trajectory tracking problem. It's a different thing, because a trajectory tracking is an external clock. It requires the system, let's say, at 0.2 seconds to be at this configuration at this velocity. That's not the same thing. It just says that I want you, when you reach a particular angle, to have this desired configuration and desired sort of like speed. So it's like an internal clock versus an external clock. So, and what I would like to say here is that, as I mentioned, this is a monotonic function with time. So you don't have to select this particular angle, but you can actually, even if you find a more complex function of variables that is still a monotonic function with time, that will actually do. And what we will do here, and so we will actually slave the actuated degrees of freedom of your system to move according to some desired evolution, which is all parameterized with respect to this internal timing variable. So it's not like an external time, as I mentioned. So this is actually like the constraint that we have imposed on the 3D piston, right? The 3D piston, it had here theta 1 and theta 2 and theta 3, and then everything was parameterized by theta 1. So essentially that was the output, and we want to drive this output to 0 so that we asymptotically make one system match the other. So this is again the behavior, again in terms of a 5-degree of freedom biped. So you have 4 torques available, so 4 inputs. So 2 at the hip, one corresponds to the left leg, the other corresponds to the right leg, and there is one also at the knee for the left leg, and then another at the knee of the right leg. So you have 4 actuators. The system has 5 degrees of freedom. So we have essentially one unactuated degree of freedom, which is essentially this angle. And then by imposing these constraints that are parameterized with this strictly monotonic quantity, essentially you can, by driving this constraint to 0, you can restrict the dynamics of your system into a lower dimensional subsystem. So what this means is basically if you take a 5-degree of freedom system and you impose 4 constraints, essentially the outcome of this process is a 1 degree of freedom system. That's what it means. And so the difference between physical constraints and virtual constraints, so by the way, in mechanics, these constraints are called holonomic constraints because they are functions of configuration variables. So if you want to enlarge the pool of constraints that you can actually impose on the system to include constraints that involve velocities, that would make actually the method much more complex. So I don't know how to actually impose such constraints. I mean, we could do it, but I don't know. I mean, the results basically of this of what I'm going to present next, they do not hold in this situation. So in the physical case, you have sort of like relationships that you impose among your joints of your system using sort of like physical parts, so gears, levels, belts. But in the virtual case, essentially you're using your actuators to impose these constraints on your system. The effect, if you see the asymptotics of those two systems, they're essentially the same. So that's for the dimensionality reduction, the virtual constraint, and these monotonically increasing parameters. So let's go into what means the zero dynamics and the hybrid zero dynamics in particular. So these systems, we have seen a picture like that at the beginning. So you have a continuous time dynamical system, and then that thing crosses a surface, which we call it a transition surface, a switching surface, which would correspond to your impact surface with the ground. And then once you cross this surface, there is a mapping, a discrete mapping, taking your exit conditions back into the continuous dynamics, right? So if you want to draw a picture of how this looks, so the basic model ingredients, so you need to have a state space that includes basically all the states of your system. And in that state space, you have a switching surface. So that's like a codimension 1 surface inside your n-dimensional space. And then you have a vector field that basically describes, this dynamics that describes the evolution of the system in continuous time. And of course, if you are to take a complete step, you have to, as you evolve continuously in time, you will actually have to hit your switching surface, which basically corresponds to having an impact with the ground. And then we have this reinitialization rule that basically takes these states and gives you a new initial condition, and the story continues, right? So you just start, then you hit the surface, going back to your continuous time evolution, evolving, hitting the surface, going back, etc., etc. So what we want to study is actually periodic orbits in which you start from a point, you hit the surface, you come back to the point, so this is a closed loop, and we want to study stability of those periodic orbits. So, yes?
Do you have another hypothesis that using walking case
yes. So in the walking case, because we use this discrete mapping, so we have like an instantaneous impact event. Essentially, we have one impact with the ground, and that's instantaneously in the sense that the other leg lifts, the previously stance leg lifts immediately, and the one that just touched the ground takes the role of the new stance leg. So it's like an assumption, but you can break that into multiple steps if you want. And in fact, this is what you would do in the running case, and this is what you do if you have a finite length foot. So the objectives, as we say, as we saw before, is essentially you have your continuous dynamics. This is the usual sort of like Lagrangian dynamics. And then you have virtual constraints that essentially correspond to those desired restrictions that you want to put in your system so that it's restricted to follow particular relationships of its coordinates. And what we would like to do is basically to design an input that will go inside here and drive this system so that the output essentially goes to 0. So that is a basic input-output control problem. And of course, if you want to design an input that will drive your output to 0, the first thing you want to do is to find out what is the relationship between the input and the output. So there is a standard procedure that one can use to do this. So you take the relationship that defines your output here, which is a function of the configuration variables, and this is the virtual constraints essentially, and you differentiate it, let's say, with time until the input appears. So remember, the target is to relate the input with the output. That's the target. So you take this relationship, you apply the chain rule, you differentiate it once, and you don't see any input appearing. If you and that's because, of course, you have second order dynamics, but if you differentiate it twice, what you see is that the double derivative of the output essentially depends on the accelerations of the system. And you know that the accelerations of the system are coupled to whatever inputs you are applying to the system through this dynamic relationship. So in principle, you know that this is an invertible matrix, so you can actually solve for the accelerations and substitute in this formula to get something which looks very messy, but it's not that messy if you actually, so you can reorganize it, and then you can basically take all these terms, and this is a notation that is being used for this part of this input-output relationship. So it's called technically the Lie derivative of H across the vector field F of second order, but we don't have to use this terminology. I'm just using this to simplify things. And then you have this other term, which is essentially again a matrix, and that's called the decoupling matrix. Essentially that matrix is what relates the input here to the output. So if that matrix is non-singular, then you have a well-defined relationship between the inputs, the torques that the actuators apply, and the output that you basically define your virtual constraints. So the whole thing takes this simple form where you have this differential equation for the output that depends, of course, on what you apply and on the state of the system. So this is the decoupling matrix again. And let's see how we can organize our controller. And the first key concept that I will talk about here is actually invariance. Invariance is a very important control concept. I mean, the very notion of an equilibrium point is an example of an invariant space. Invariance intuitively means that if you start your system from that point, essentially it will stay at that point for all future times. So that's the notion of an equilibrium, basically. So an equilibrium is an example of an invariant subspace that is composed by one single point. And so what we would like to do here is basically to impose the virtual holonomic constraints that we had based on our original sort of like design. And we have this relationship between the output and the input. So if this matrix, which we called it the decoupling matrix, is a non-singular matrix, which means if you can invert it in a neighborhood of this point, which would correspond basically to your equilibrium point or to your desired periodic orbit, if you can invert this matrix, then you can compute this input basically, which if you take it and you plug it into this equation, essentially this matrix will cancel because they are the inverse of each other, right? Then this term here will actually cancel with this one because there is a minus sign in front, and the whole thing will result down to something which is very simple, and it's y double dot equal to 0. So this is why, I mean, people are calling this method as a feedback linearization, because you are using feedback to compute terms in your control laws that will essentially result in a very simple linear system. So why is this important? Because what it says is that if I start my system with initial conditions that have 0 output and 0 time derivative of the output, then the system will continue evolving with the output being identically equal to 0 if you use this input. Is there any question that you would like to answer this? Or? Oh, okay. So this controller, and this is the invariance principle, right? So if you start with initial conditions that satisfy your output here, and you implement this decoupling controller, essentially what's going to happen is that your output will stay equal to 0 for all future times, if it's a continuous time system, of course, right? So this is a controller design for achieving this invariance property. So let's see what this means in pictures. So we had our state space, this state manifold, and we have the continuous dynamics. So by, oh, it's there, okay. So by, then we introduced our virtual constraints, which are basically functions of the configuration variables. And then essentially we define a surface in that state space, which includes all the states that are compatible with my output being identically equal to 0. So these are all the states of the system that are compatible with y being equal to 0 and y dot being equal to 0. So it's a subset of your state space, right? And then what we have seen is that actually, let's just call this, I mean, this is the zero dynamics surface, and that's the first sort of like term of the hybrid zero dynamics is the last part of this term. This is the hybrid zero, and this is the zero dynamics surface, and it contains basically all the states that make the output identically equal to 0. So that's why it's called zero dynamics. It's basically the output is being equal to 0. And then we have designed an input based on this invertibility of this decoupling matrix. And we have seen that this input makes the system invariant, which means that if you start from a point which satisfies the constraints, so that basically it is a point that lies on the zero dynamic surface, then you are evolving continuously in time without really leaving the surface. So that's the notion of invariance in our particular sort of like setting. You start from a point on that surface and you're evolving along that surface. What this means is essentially that if you start from a point that satisfies your constraints, you will keep satisfying your constraints. So that's what it means. So this basically controller makes the surface invariant, as I mentioned, and technically the restriction of the dynamics of the system on the surface is essentially the zero dynamics of that system. So what is the zero dynamics? Is basically the dynamics of the system that are compatible with the output being identically equal to 0. So, is there any question? Yes, please.
So, invariance principle works, but what if there's a disturbance or?
Yeah, we will see that. So I'm talking about exactly. So I'm talking about the invariance first, and then I'm going to talk about attractivity, how to bring the state back to your zero dynamics manifold. So all right. Okay. So there is a problem here, and with that slide, I would like to introduce the notion of hybrid invariance. So okay, I mean, according to classical control theory, you can actually design those surfaces. You can make them so that when you start from the surface, you continue evolving on the surface. But in our case, remember, if you are to take a step, you have to hit the ground, right? And that means you have to hit your switching surface, and that will reinitialize the state, right? So what happens is that you have, again, this system. Let's say that this system is actually in closed loop with your decoupling controller, what makes the surface invariant in continuous time. But you have to actually hit the switching surface, which is the impact, which basically corresponds to the impact with the ground. And then once you do this, actually, yeah, and you can actually visualize the surface here. So this blue surface essentially includes all the states that correspond to your leg hitting the ground. So this red surface is basically all the states that correspond to your output being 0, your constraints being satisfied. This blue surface corresponds to all the states that correspond to hitting the ground, basically after one step. So, and then you have this discrete update, which takes your exit condition from the motion. It basically takes it through the impulse map and gives you an initial condition so that you can keep integrating your differential equation. So what this means is that once you hit this surface, you have this mapping that takes your state from here into an initial state here. Now the problem is that this initial state may not be part of the surface. So the very nature, the very hybrid nature of the system essentially breaks invariance in continuous time. So you have to take extra caution to actually designing your system so that this state comes back to the manifold, comes back to the zero dynamics surface. So, and there is a theorem, and actually we will see how to do that. I'm just going to, this slide was just to show you that whatever you design in continuous time, when you have a hybrid system, you have to take extra care that certain concepts are being preserved by the hybrid nature of the system. So, and what this theorem roughly says is that you can design essentially these surfaces so that this condition is always satisfied, which means that whenever I leave the ground, whenever I hit the ground, my initial conditions essentially are given on the zero dynamics surface. So this is the notion of hybrid invariance, and the resulting dynamics is called the hybrid zero dynamics. So, and this goes back to the question of attractivity, basically. What we have seen so far is basically how can you ensure once you figure out basically what the constraints are, and once you basically can ensure that you are converging to these constraints, you're satisfying these constraints, how you can ensure that you can stay on this manifold. So this slide here, it basically talks about attractivity. Motion is continuously perturbed. You're not going to be on that zero dynamics surface all the time. Somebody's going to push you, there's going to be an obstacle, all sorts of things. So you may start outside of the surface. So what can you do to converge to that surface? So that is attractivity. And essentially, it's very similar to what we did before. Instead of U star, though, you have this U, you have this inverse of the decoupling matrix, you have these other terms that basically cancel out, and you add this term here, which is essentially a PD control law. It's nothing really complicated on this term here, but you can take this input now, plug it into your input-output relationship. This matrix with this matrix is going to just disappear because they are one is inverse of the other. This thing here, this term here, is going to actually cancel out with this, and eventually your equation is going to be looking like this linear system. So again, that's an example of a feedback linearization where you use feedback to compute a control law. That's a function of feedback. I mean, it involves knowing the state basically of the system, and you use it to compute this control law so that you arrive at this linear form. Now, this linear form has this thing as a solution, and basically, physically or intuitively, what it means is that if you pick your gains basically appropriately, which means if you make these things positive numbers, essentially your output is going to converge to that zero dynamic surface. So what we have seen so far is two concepts. One of them has to do with invariance and hybrid invariance, what means basically to satisfy your constraints identically. Invariance and hybrid invariance. The other one is, what if I am perturbed? How can I return back to my zero dynamics manifold? So these two conditions are basically the very important conditions that allow you to impose enough structure on this system that you can do actually proofs, and you can show that the lower dimensional system essentially governs the higher dimensional system. So far we have seen principles of dimensionality reduction. We have seen how to impose those constraints via invariance and attractivity of those surfaces. So, okay, let's see, I mean, just sort of like a sketch of what's going on here. So basically you want to stabilize a periodic orbit, right? So this is your periodic orbit. So essentially you have a continuous time, you hit your, this is your impact surface, you hit the surface, so that's your Poincaré section right there. Then you're having your delta mapping here. It takes the state right prior to hitting the Poincaré section into a state on the Poincaré section right after impact, which lies somewhere here, and then the system continuously evolves. And you know that to describe basically this periodicity of the system, you can actually derive through integration this Poincaré map, which is basically here. And then you usually, what you do is basically you want to linearize this thing in MATLAB, and you want to basically compute the eigenvalues, and if all the eigenvalues are within the unit disk, then you can claim local stability, local exponential stability. So it's all local here. And so what we have gained with this extra structure that we impose on the system is basically that we can bring our Jacobian of the Poincaré map in this form that you have seen at the beginning. Now let's see this form again. So what we did is basically we have introduced a surface which we called it the zero dynamics surface. And we know that if the system, if the periodic orbit is part of the surface, essentially you start here, you will evolve compatibly with Z, then you hit here, then you get your hybrid invariance to bring you back to the surface, and then you continuously doing that. So what you do with this extra structure, it's basically that you reduce the dimensionality of your Poincaré map. So how this happens is that now the Poincaré map is basically defined on the intersection between your Z surface, which is the zero dynamic surface, and the switching surface. So this system here is essentially the reduced Poincaré map, right? It's a Poincaré map that actually has to do with the, it's defined on the intersection of those surfaces, not on the entire, not on the entire state, which is basically this case here. And, you know, I mean, if you go through these papers, you can see that it's just an application of the chain rule that you can actually use to bring the system in this form. So we have the full order Poincaré map, the reduced order Poincaré map, and then we have these extra terms here, which correspond to the transverse dynamics. But these extra terms involve, as I said, this parameter epsilon, which has to do with the gains, and you can actually pick these epsilon parameters to make this sufficiently exponentially converging to suppress basically any divergent behavior that we get from this term, to push all the eigenvalues that are associated with this term here inside the unit disk, so that the stability property of your Poincaré map here essentially is identical to the stability of this term. So this is the dimensionality reduction via sort of like zero dynamics manifolds, invariance and attractivity, that you can actually bring the system down to this form. And in this form you can read basically that, you know, my full order Poincaré map essentially has the same stability properties with my reduced order Poincaré map if I pick my design parameters in the right way, right? And actually, I don't know if we will have actually time to show this, because it's already 5 minutes before 12. This thing, you can actually make it equivalent to the spring-loaded inverted pendulum dynamics. So it's just like having here a spring-loaded inverted pendulum Poincaré map that basically drives the properties of your overall system once you are designing any transverse dynamics that you have in an appropriate way. Yep.
Please explain the top right term in the matrix.
The one that's in the red box, right?
No, the right to the...
Oh, this one?
Yes.
So this one is a coupling term that basically, you know, I mean, it's there, but it doesn't play any role in the stability analysis, because the eigenvalues of this system essentially are the union of the eigenvalues of this subsystem and this subsystem. So stability-wise, this term does not play any role, right? But I mean, it basically, this term, what it describes is the coupling between your zero dynamics and the transverse dynamics. So if you're not exactly in the zero dynamics and you are converging to it, there is a coupling between whatever your outputs are and how fast they converge to the origin, and it's basically the coupling between these two terms is coming from here.
Okay, thank you.
Yep. Well, no, there's no particular reason, and actually you can actually take your Poincaré section to be any section as long as it satisfies certain conditions, right? I mean, it's transversal to the orbit.
This just makes it easier?
No, this just makes it, I mean, perhaps a little bit more intuitive, and that was the first choice that was done, but I mean, mathematically you can actually use any other section along your orbit. Are there any other questions with respect to this sort of like structure here? And this is a result, remember, of two things: hybrid invariance and attractivity. Two things. So then, you know, I mean, this is basically the structure of the controllers and how they kind of like, you know, give rise to these proofs, etc., etc. But let's just see how you can actually design outputs and holonomic constraints. We've seen how to impose them on the system, but we haven't seen how to actually design gates using this particular situation. So here is basically what happens in gate design. So you have basically your output, that is the difference between the variables that you want to control, and that could be sort of like a subset of your configuration variables, and some desired evolution that is parameterized with this parameter theta that we have seen. It's a strictly monotonic quantity, monotonically increased quantity. So here, okay. So here is exactly where intuition from the reduced order model enters the picture. So in essentially how you design those outputs. And we will see what this means in a second. So here is your desired evolution. The parameterization is basically you have your gate phase. Remember that we have seen that you slave the entire system with respect to an internal parameter, not time. There is no trajectory tracking here. And then you have free parameters that you can choose based on sort of like to achieve additional sort of like specifications. So let's just go through an example on how you can actually design this term here. So this is a 5 degree of freedom bipedal system with 4 actuators, and that's actually an example that's maybe, that corresponds to the rabbit robot. There's no spring still. So you have 4 actuators, 2 at the hips, left and right, 2 on the knees, left and right again. You have 5 degrees of freedom, and essentially one of them is unactuated, right? So you have, you know, the thigh angles with respect to the torso, you know, the angles of the knees, and you have also the unactuated degree of freedom. And essentially what you have is 5 degrees of freedom, 4 actuators, one of the degrees of freedom has to be unactuated. So since you have 4 actuators, you can actually impose 4 constraints, which are given here, to slave those variables to move according to those constraints. So you can actually define your output to be the difference between, you know, the angle of the knee, the left hip, the right knee, the right hip, with respect to all these constraints. So theta q increases monotonically with time, and that alpha here, as I mentioned, is basically parameters that are free to choose from where these parameters are coming. So the way you can use actually, and let's just take one of those variables, let's just isolate the left knee, if I remember correctly, right? Yeah, the left knee, the first one, the first component of this output. And basically you can have this thing to be a polynomial function. So this is nothing more than a polynomial. It's actually a polynomial expressed on a different basis. It's the Bézier polynomial. So essentially what this gives you is the desired evolution of this sort of like knee, left knee angle with respect to this parameter. And remember how, I mean, these are the parameters alpha essentially, and you can do that for all the legs, and you get like all these extra alphas. And then you have a parameter that parameterizes basically this polynomial, and that's actually the difference. So it's a parameter that takes values between 0 and 1 in the nominal gate. That's only in the nominal gate. If you're off the nominal, this may go off. But basically it's the difference between theta q and the angle at which you hit the ground, which is here. And the denominator is basically the difference between the angle that you exit, theta minus, and theta plus here. So essentially this term, so once you hit the ground, this is equal to theta, this is equal to sort of like theta plus. So essentially you start from s equal to 0. Once you exit, is basically this is equal to theta minus just prior to exit, so that's equal to 1. So it gives you a parameterization with this, with respect to these terms. And these Bézier polynomials are, you know, you can use various functions here. You don't have to use these types of polynomial parameterizations. You can actually use, I don't know, other types of polynomials. You can use Fourier functions or whatever you want to choose. But these have an important, kind of like a property that will be handy when it comes down to hybrid invariance. So you do that for all the legs, and you stack all these polynomial coefficients into a single variable, and then the difference with whatever we have seen so far is that everything becomes a function of these parameters, right? So now everything becomes a function. So each time you change this alpha, which includes all the polynomial coefficients, you're essentially changing the shape of your holonomic constraints, of your virtual constraints, and essentially what you do is you're changing the shape of the zero dynamics surface. So the way you actually, you can pose the problem basically as a constraint optimization problem, and that's actually one of the biggest disadvantages of the method. And of course there is no claim of optimality here. As long as you can find something that actually would work, that's good enough. So because remember, I mean, we restrict everything to a particular class of functions, to a particular output, so there's nothing that has to do with true optimality in terms of how much energy you need to take a step and all these things. But you can actually, to make the problem tractable of selecting basically those polynomial coefficients and those variables, essentially you can select a performance index. In this particular case is to minimize the basically the actuator inputs over a step length, and you impose an equality constraint that has to do with periodicity basically, and you go through, you can impose other equality and inequality constraints, and you go through solving this problem. That's actually a bottleneck, and this is one of the main disadvantages that you have actually with respect to this method. Now, I don't know if I have too much time to go on this, because I would like to actually talk about the yeah.
Here you're minimizing the nominal U. Is that the
yeah, that's the nominal. It doesn't have to do with any
no feedback for this. This is just minimizing the nominal U for when. Okay.
Correct. Correct. So that's why, as I said, the optimization is just to find an orbit that is reasonable. It satisfies all the physical constraints that you have on the problem, and that's it. You shouldn't make any claims of any type of optimality or any type of off-nominal behavior based on these things, right? So, okay, I'll skip these design things because I would like to enter basically into the last part, a little bit talk about springs. So, okay, that's a video just to motivate it. So the problem here is that, once you're doing like these methods, essentially you are ending up with, you remember you have like n degrees of freedom, you have n-1 actuators. So when you are imposing n-1 constraints, essentially you are left with 1 degree of freedom system, right? That 1 degree of freedom system is not rich enough to include compliance. Like remember, the spring-loaded inverted pendulum is a 2 degree of freedom system. So if you want to have your hybrid zero dynamics being 1 degree of freedom, that cannot be compliant. So the method, in fact, was very successful in working, but when Eric and Jesse have tried to implement it in running, it didn't really work. Yes?
Stabilizing the dynamics, transport dynamics can have a compliance. It's not direct relationship, but your PD controller can impose.
Yes. But the thing is, like, the PD controller is a blind sort of like, it just is an output, and it feedback linearizes the system to actually drive that output to 0, which means in doing this feedback linearization procedure, you may destroy sort of like dynamics that work for you in doing that. And that's actually one of the examples, right? You have this spring-loaded inverted pendulum system, which you have to store energy when you hit the ground. The knee bends, basically, you store energy, and you have to coordinate your system around that. So essentially, you have to see this as your reduced order dynamical system, as your lower dimensional system, and coordinate everything around this thing so that you can actually jump around according to this. So this is kind of like a compliant version of the hybrid zero dynamics. I guess this is as close as I could get to biology. Maybe this picture over here. So essentially, what I would like to say here is basically that you have a hierarchy of models, right? You start from the slip, but the slip is not strong enough to actually control this system. Then you go into a slip with an attitude, as Noah was saying yesterday. So you have this central, so this is a slip which you have a torso, but it's kind of like a symmetric situation where the leg force goes through the center of mass, right? And then you have this A-slip. Back then I didn't know how to, this has various names, I guess. So this is the asymmetric spring-loaded inverted pendulum. So I'll just, that's correct, right? VPP, whatever, like all sorts of things, right? And then, I guess you go, the running is different from walking. You have to go through stance phase, you have to go through flight phase, lift off, fly, touchdown, etc., etc. So the model basically has massless legs, is again a slip model, actuated slip. Again, we have an actuated pin joint. In flight phase, we can actually control the angle of the leg with respect to the torso and the leg length. And we have also some control inputs so that we can actually use our method to impose basically the spring-loaded inverted pendulum. So it looks like a system of this sort, right? So that's a little bit different. You have your stance phase dynamics, then you take off, then you have a flight map, then you go into the flight phase. It gives you initial conditions for the flight phase, then the flight phase evolves, then you hit the ground, then you have another map that gives you initial conditions for the ground support, and then you integrate and you go on, so on and so forth. Now you can integrate this flight phase in even analytically to find something which is technically called a flow map. So essentially what this thing is, it takes the entry conditions to this surface and the touchdown angles essentially, and it gives you the exit conditions from that flight phase. Because of course whenever you take off, the point at which you will hit the ground does not depend only on the initial conditions, but depends on how you set your leg. And in fact, this is actually a very important control parameter, right? So then if you do this integration and you compose basically all these mappings into delta, you get a system which looks like the systems that we have seen, with the difference that this doesn't describe impacts anymore. It's just a general reset mapping. So the objectives basically here, so we want to create orbits that are stable. We want to respect the constraints, and of course the method is that you can take a system that you know that it possesses nice orbits in these terms, like it respects constraints, it actually have very natural sort of like bouncing motion, and try to see if you can actually embed this system within the dynamics of the A-slip. So the controller, in order to do this, it actually works on two levels. It has a continuous time control component. And effectively when you close the loop in continuous time, essentially your system is going to be looking like a spring-loaded inverted pendulum, and we will see what this means precisely. Actually, if we have the time, do we? Maybe 5 minutes. So, and then there is a discrete component that basically sees something that is the spring-loaded inverted pendulum. It's not like the complicated A-slip. Is the true spring-loaded inverted pendulum, and we can use all these sorts of event-based controllers that have been produced in the context of the slip to actually make them relevant to controlling something which is more complete if you think of thumper. So the situation is similar with what I just described. You know, you have this stance dynamics, and you have two inputs acting on your stance dynamics. So it's a hip torque and it's a leg force. And essentially, the trick here is that you will not use two holonomic constraints to impose, to use actually your two inputs to impose those two constraints. You will just slave one of the inputs and leave the other free for subsequent design. So here we actually pick the hip torque, which is this U2, and we design and we want to stabilize the pitch, basically make the pitch constant, equal to a particular value. And you know, that's again equivalent to actually defining these zero dynamic surfaces. You can actually use the standard prescriptions that we discussed to actually make them invariant and attractive. And when you do this, you're left with a system like this. You still have one input that is available for you to do control, right? And it turns out that mathematically, if you put this input as a function of the spring-loaded inverted pendulum force, leg force, and this is essentially a projection term, essentially what you do is that the dynamics of your asymmetric hopper, compatible with your output being equivalent to zero, which means after you converge to a constant angle, the dynamics of this hopper is indistinguishable from the dynamics of the spring-loaded inverted pendulum. So what this means basically is that you fix the attitude of the torso, right? And then you let the center of mass be taken care by the slip. So you just use one input to fix the torso pitch angle, and then the rest of it, I mean, the hopping basically, the center of mass hopping is essentially the spring-loaded inverted pendulum. You can get also hybrid invariants on this. You can actually implement Raybert's controllers. And there is a benefit in that, in the sense that if you actually use the method directly, and that's what I'm saying, like, we shouldn't just try to use the method directly. The thing is like how you design your holonomic constraints and how you actually, it's not how you impose them, it's how you design them. If you actually do a blind application of the method, remember we had 3 degrees of freedom, 2 actuators, we can actually have the system be a 1 degree of freedom system, right? The problem is that when you get into transients, you know, I mean, this is a model that doesn't have compliance, is in 1 degree of freedom hybrid zero dynamics. This is a model that is you know, a spring-loaded inverted pendulum model, which basically has compliance. And you can see that, I mean, this is the reaction from a perturbation that is a 6-degree perturbation in the pitch. And the problem is when you go into leg reaction, ground reaction forces, right? I mean, if you see the rigid target model, the lack of compliance in your hybrid aerodynamics give you this weird shaped type of forces, right? Precisely because your system is 1 degree of freedom and it only describes the fore-aft motion of the system. It doesn't capture any compliance that you can have, that you want to have actually in the system, because you just killed it by just using your extra holonomic constraints to actually remove that from the system. If you see the slip embedding, this looks like very much like the spring forces that you would expect to have in the slip embedding controller. And in fact, they're very close. I mean, if you superimpose it with the spring forces, they're actually very, very close. And, you know, this gives you, of course, very, I mean, huge benefits when it comes down to actuator effort. And the reason why this is happening is basically that you are taking the force of the slip, of the A-slip, of the asymmetric system, and you are making it something that's compatible with a central force that is a spring-loaded inverted pendulum force that goes through the center of mass. So this is something like the VPP, except that it's not as smart perhaps, because you pick your VPP point to be the center of mass, which doesn't make any sense. But of course in this case, because you have the hip torque, you can actually do it. So anyway, perhaps I could close with this slide. So the thing is, like, the key idea here, and perhaps closing the loop with what I mentioned at the beginning, is that I mean, typically we have these lower dimensional systems that we know that they encode some certain desired behaviors, right? The question is, like, how can you make them relevant to a system which has higher dimension? So how you can actually reduce this dimension and make it equivalent to these reduced order models, to these templates. So the way we've seen, I mean, through this hybrid aerodynamics method is basically to use feedback to impose certain constraints on the evolution of your actual system so that its joints or its excess of joints are coordinated with respect to a lower dimensional system that, in the particular example that I showed you before, could be the spring-loaded inverted pendulum. But of course, in the general case, you have to think a little bit more on how you would design this thing. So I think I don't, yeah, I mean, jumping from one to the thumper. So anyway, I would like to stop here, and those who want to actually go through just looking into the MATLAB files, we can actually do it. But I guess if anybody wants to ask any questions with respect to what has been presented. So it's a little, you know, I try to do it sort of like I show enough of the mathematics. I guess this would be like maybe a hard presentation to go through in a conference, especially in a conference that includes people who do not necessarily work on nonlinear control systems, but I wanted to have all the information there just to spell it out explicitly. So, yeah, questions, if you want to, yeah.
So you said that there is still hybrid invariance in case of running, for example, when there's transition between.
Let's just say with respect to this particular model of running, right? I mean, right. It's not a general thing in running. I mean, thumper is not hybrid environment. You have to do control to actually do it. Oh, I see. Enable the same thing.
So in general case, there is not a guaranteed mapping from zero dynamics.
You can design. Actually, I skipped that part because there was not enough time. You can actually design, and we can discuss it if you want. You can design those coefficients basically that you have in your Bézier polynomials, so that each time you hit the ground, you have an event-based controller that updates these coefficients, which means it deforms the surfaces in a way that your initial condition lives in these surfaces. But I can show you what I mean more precisely using those slides that I skipped.
I have two questions regarding the key ingredients and prerequisites to apply the presented approach. The first question is, how good does the mathematical model of the motion dynamics have to be so that you can apply it? Mm-hmm. The second question is, you have the control appearing linearly in the system, in a specific form in the vector field, the U, linearly. The question is, what happens what are you doing? How applicable is it if it's non-linearly in the system?
I will have to ask you a little bit more about the second part of the question, because I'm not sure I understood what you mean. So it's after the... Yeah.
The vector field is f of x plus g of x times u.
Yes. Oh, it's affine in the control. Yeah.
Requires a specific way how the u appears in the system. The second part of the question was what happens if this is not linearly?
Yeah. Then I mean it's not, you know, it's not an easy problem to solve if you have a general nonlinear system where the u appears in your equations in a nonlinear fashion. So I mean in these mechanical systems you do have your u appearing in a linear fashion because of the way the dynamics works out when you do the model, the Lagrangian model. But in general, you have to do, I mean, this wouldn't carry through as easily in the general case. So with respect to your first question, how good your model has to be. So, I mean, the better it is, the better the method is going to perform, right? So, I mean, it's good to have a good model. But that's, you know, once you're introducing feedback, and in fact we strive to actually have good models of these robots. But the models that will never be perfect. I mean, all these assumptions, you know, with the, you know, instantaneous impact in the walking, or all these assumptions are actually kicking you off from reality. But when you're implementing the controller, the feedback is giving, you know, robustifies the system enough so that mismatches that you have with the model parameters, or even structural elements in your model that you didn't encounter, essentially enable the system or the robot to go through, you know, a meaningful walking or a running gait. I mean, so the short thing is we should have, or we try to have, as good models as possible with these things. But the fact that you can actually experimentally implement these control laws on very complex robots for which you will never have a perfect model shows that the method is robust enough to accommodate uncertainty that comes from your model. I don't know if that answers the question, and yeah, for the other part I think yeah.
So,
okay.
Great presentation, and really,
you
really
think so?
clear.
I think it was very detailed, maybe
no, I've read the papers.
Inappropriate for the
I've read the
audience.
papers, and your presentation helps really a lot to understand properly. It was perfect. One question is, can you give us an intuition what you have to add to handle non-instantaneous contacts, a bit longer contacts, possibly with a rotating foot, like even a moving contact point? I guess you have to work at two levels, both the simplified model and the whole.
So essentially, I mean, the mathematics carry through as they are essentially because you can reduce this. Think of the case of running. Although it's different from what you're asking, but think of the case of running in which you have two continuous time phases, not just one and a reset. But so if you sort of like, you can always integrate extra phases and essentially focus on one and having a discrete map that gives you basically, I mean, this is your base, let's say, phase, and then you have a mapping that brings you back to that phase that essentially is an integration of all the other phases that you can have. And actually this is what we've been using for Thumper or Mabel, because you want to have control over all the separate phases and you want to be able to change things in all the separate phases. But you can do something like that through integration, and the theory should carry through. I mean, it's...
I was comment and maybe questions at the same time on the previous point.
Yeah.
Is the transition is basically your equation of motion transition. So transition, let's say a rubbery foot, your equation motion change doesn't necessarily means your change in dynamics is abrupt.
Yeah, it doesn't. I mean, well, if it is an impulse, you don't. I mean, in the simple sort of like impulse model, essentially your configuration is invariant under that, but you have a jump in the velocity.
But if your model has let's say at the end of the foot you have a massless spring at the end.
Yes.
And then
yes,
you can take care of any range
you
of
can,
transition, right?
So in one case, so in the A-slip case, in fact, that's the case. That's the because you have a flight phase, you don't have any losses. So all these mappings that take, you know, stance coordinates to flight coordinates, or these resets basically that we have seen, all these things are not abrupt changes. They do not correspond to any abrupt change in the system. But in the walking gate, if you want to include impacts, you will have a jump in the velocity when you do that. If you don't have a spring taking care of that thing.
You can always add one more spring.
You can always, you can do it, and
make it complex.
But of course, you know, you have to go through, because it depends on you know, the orientation of the loading that you have. You can still have impacts. For instance, if you have a linear spring, but you have like a, you know, not a hip spring, you can still have, no.
So I'm thinking about this. If I had a system that you had designed with hybrid zero dynamics, if I did system ID, I don't think I would be able to tell what the zero dynamics manifold was, because the convergence rate to the manifold and along the manifold aren't necessarily sort of ordered in some sense. Is that correct? Or normally is the convergence within the sort of target dynamics manifold, do you typically tune that to be a lot slower or a lot faster?
So yes, I mean, you can, you have a design parameter basically, you know, that epsilon thing that was participating in these formulas, that essentially you can pick so that you make the convergence to the zero dynamics manifold as fast as you want, provided that you are compatible with, you know, constraints that are coming from actuation and all these things, or friction cone limitations. So the proof of this theorem, basically, you know, it's a singular perturbation argument that you have to do, which means that in the limit as epsilon goes to 0, which is like the high gain limit, but then, you know, the result holds for any positive epsilon, or for a positive epsilon, or it tells you that there exists some setting for which stability is guaranteed. To say it like that, I can be more specific in what I'm saying.
But typically you're saying that you'll wind up with pretty fast, you know, much faster convergence to the dynamics. Those would be the sort of
fast enough. Yeah, you can.
But probably faster than the convergence once you're on the target dynamics. So that you would, from data, I could make a good guess. Say, for example, looking at the Poincare map, I could look at eigen subspaces and make a guess that, oh, these are probably the target dynamics, and these are the
So you need to have some sort of time separation, if that's what you're asking, yes. I mean, you need to be able to sort of like the time at which you converge on the zero dynamics manifold needs to be fast enough. Otherwise, you will diverge. Otherwise, the eigenvalues of in this triangular matrix, the eigenvalues that would correspond to the transverse dynamics will actually be above 1.
Okay.
Yes.
I have a question regarding the use of this methodology when you are coming from flat terrain to rough terrain, where these virtual constraints that were imposed before, maybe they are not adaptable anymore to this new environment. So,
So that's a very good point. I mean, so there are many things that you can do, and in fact, there have been some implementations of Hayward Park. Actually, did a very beautiful implementation on the case where you have like unexpected, very big ground height variations. So the key there is actually and actually, you know, I'd like to generalize a little bit and say that the success of the method on the robot, it's basically that, yes, there is all this formal framework on how to impose constraints and stuff, but it gives you enough freedom to incorporate intuitive things. Otherwise, it wouldn't, if you think of it as a control method, I take it out of the box and I apply it and the thing is going to work, it's not going to work. You have to go into sort of like figuring out how to incorporate other elements. So there you can actually, you know, just like what I did, I just used one of the inputs for the A-slip and then kept the other to just redirect the force to make it go through the center of mass. You can actually do similar things to change compliance in your system. So to have like a compliant type of controller using extra, or to update parameters in your polynomial that would actually take care of similar things. And you have to go through this if you are to walk on rough terrain, basically. So you can actually use it in terms of like there is this position control that you have ready and works out of the box, but then if you want to incorporate, you know, any stiffness control things or any other sort of like algorithms, then you have to be smart about doing it.
So basically we can say the feedback term in the Jacobian you were showing the part, the reduced part, it has the open loop behavior.
Okay, yeah. Mm-hmm.
Like the PD feedback there, this PD is working well to regulate the system back to the virtual constraints you were giving, and if the virtual constraint, if the environment changes, it's not about the PD anymore. We need to go to change of the polynomial.
Well, you know, it's a combination because the PD, you know, it's going to throw you off the surface. So the PD can give you as much as converging to the surface, but maybe you need more. For instance, in running, you know, converging on this surface doesn't mean much. I mean, you want to use your touchdown angle control, and actually there was not much time to present that here. So that means basically you want to not only deform your surface at the entry condition so that you have these hybrid invariants, but you can actually deform them at the exit condition, which means basically you have control over how your leg angle is going to hit the ground the next time. So you have to combine. I mean, it gives you, as I said, enough freedom to actually use empirical sort of like methods and things that people see when they are working on spring-loaded inverted pendula and all these things.
Thank you.
Okay. There was one more question. Yeah.
So thank you for the nice tutorial. I'm interested in the application in robots. If you
which robots? Excuse me.
For example, if you have a segmented leg.
Yeah, in the Maybell and Thumper. Yeah.
Kinematic singularities that you might face when you don't have a mechanism that prevents you from this. So
yeah. So
in the piston example, for example, you are constrained by the mechanism. In the 1D example, but in the 3D example,
that's indeed true. I mean, and you can have singularities that are not only associated with sort of like, let's say, kinematic behavior of the robot, but you can also have singularities that are associated with the method itself. In the sense, you have to invert that decoupling matrix.
Okay.
And what if, in the neighborhood of your equilibrium orbit, or in the neighborhood of your periodic trajectory, what if that matrix is not invertible? So these are constraints that actually typically go into the optimization problem that I mentioned on how to pick parameters and states. And essentially what you do is you do an effort to design your nominal orbit so that the system stays away from these singularities during the nominal orbit, and hope that, of course, you know, the perturbations that you're going to get, they're not going to put you into a regime where these singularities emerge. So far the method has been successful in the sense that it gives a lot of, you know, sort of like a large, let's say, domain of attraction of those orbits. But of course, you know, if you fall into a singularity, it's not going to work.
So
yeah,
you're not 100% aware, but you can avoid it.
There is no explicit sort of like, let's say, saturation function or something that would actually keep you away from these things when you're designing the controller.
Okay.
But you can, in the optimization, you can actually put it as a condition.
Okay.
And then, you know, if the perturbations push you, you know, I mean, robots can fall, and actually these robots have fallen many times. I mean, humans can fall too, right?
Sure.
Perhaps the most important behavior would be just to make these robots stand up again alone, right?
Okay.
Because they will go through falling down. And
okay.
All right. Other questions with respect to this part? And
For the feedback linearization part, I was wondering, maybe you have seen this approach from 2005 by Martin Bohler for projected inverse dynamics. Not include, like not be concerned about the stance, the force that we have in the stance phase. I was wondering if you have used this for the feedback linearization part so far.
No, we haven't used that thing, but I know that, I mean, it would be interesting actually to see if there is any non-empty intersection, and actually if we can actually take tools from this work and use them into this framework. It's an interesting, it's a very good suggestion, and I think it's right.
I just have a very short comment. Like you do the constraint nonlinear optimization on the simulation.
Yes.
And then you port the results on the robot. How that process, like how long is that process? What's your experience with that?
What was the question?
Like transferring the results from like the nominal. Like
so in Rabbit, it was like a method that worked out of the box. Like you took this optimization thing, the polynomial, you just run it, play it on the robot, and the robot has this behavior I just saw. It was like minimal error, trial and error, and that was actually one of the selling points of the method, which was very successful in this context. Now, once you go to Mabel, you still, you know, I mean, you can still design certain things in simulation, and you don't, but you mostly play in simulation to find out the good trajectories that you need to have. You don't do the trial and error on the robot, but the robot may fail, so you go back in simulation and you redesign and then you implement. So Mabel is a different story. It's much more complex, and basically the fact that we have introduced heuristics to make this method successful is that, you know, you still have work to do in order to actually have something that works as good as in the walking case, right?
Okay, so thanks again.
Thank you.